You find yourself on the bridge of a cargo ship in the midst of the North Atlantic. January. A storm. Waves reaching 10 to 12 meters. Serious but not unprecedented. The ship is designed for such conditions. It rolls, rights itself, plunges its bow and resurfaces. Just another day in the winter crossing. The officer on watch is accustomed to it. The autopilot maintains the course. The radar displays the usual scene, chaotic reflections from waves within a few miles. Nothing out of the ordinary. And then, there it is ahead. Not a wave, a wall of water. Vertical, dark, with a frothy crest at a height that should not exist here. 25 meters, 30, the height of a 9-story building. One rogue wave amidst a 10-meter storm. It doesn't fit into the surrounding wave pattern. It has no predecessors. There is no series of building waves before it. It has appeared out of nowhere. In just a few seconds, it will strike the ship. But here's what most people don't understand. A rogue wave is not just a very big wave. It's not the upper limit of a normal distribution. It's an anomaly. A wave whose height exceeds twice the significant wave height of the surrounding sea state. It disrupts the statistical models upon which all marine engineering is based, from hull strength to freeboard height, from deck cargo securing calculations to oil platform designs. A ship navigating through a 12-meter storm is designed for 12-meter waves, with a safety margin. Its hull, its fittings, its stability are all calculated for a specific maximum. And when a 25-meter wave suddenly emerges from that storm, the ship is thrust into conditions that no engineer, no classification society, and no calculation model ever anticipated. The forces acting on the structure exceed the calculated limits by several times, in mere seconds. This is precisely why ships disappear. They don't just sink in a storm, they vanish. Without a distress signal, without debris, without a trace. The crew has no time to communicate anything, because the time from spotting the wave to impact is less than a minute, sometimes less than 20 seconds. Today, we will delve into the physics of rogue waves. Where do they come from? Why are they impossible to predict? What do they do to a ship? And why the balance between vessel strength and the economics of global shipping leaves the fleet vulnerable to a phenomenon that, just 30 years ago, was dismissed as sailors' folklore. Let's begin with what constitutes a typical ocean wave. The surface of the ocean is a superposition of thousands of waves occurring simultaneously. Waves of varying lengths, heights, and directions, generated by different storms in different parts of the ocean. They overlap, combine, and cancel each other out, creating a chaotic yet statistically predictable pattern. The key concept here is significant wave height, denoted as HS. This is the average height of the highest 1/3 of waves in a given wave field. If HS is 10 meters, it's a serious storm, but one expected in the winter North Atlantic. In such a storm, individual waves can reach 13 to 15 meters. This fits within the standard Rayleigh distribution, a mathematical model that describes the probability of waves of various heights occurring. According to the Rayleigh model, a wave twice the height of HS, 20 meters in a 10-meter storm, should occur roughly once in every 10,000 waves. It's rare, but theoretically possible. Engineers take this probability into account during design. But here's the catch. Real-world observations show that waves significantly exceeding double H's occur far more frequently than the Rayleigh model predicts. Not just 10 times more often, in some conditions by orders of magnitude. Waves reaching 25 to 30 meters in a 12-meter sea state are not just statistical outliers. They are a distinct physics governed by different physics. Until 1995, the scientific community viewed rogue waves with skepticism. Sailors spoke of walls of water 30 meters high. Scientists responded, statistically, such a wave could occur once every 10,000 years. You're exaggerating. On January 1st, 1995, everything changed. The oil platform Drona in the North Sea recorded a wave using a laser altimeter. Its height? An astonishing 25.6 meters. The surrounding wave activity was around 12 meters. That's a ratio of more than 2 to 1. This was an instrumental, indisputable measurement. The Drona wave transformed a sailor's tall tale into a physical fact. Where do they come from? Why does the ocean, which typically obeys statistical laws, suddenly generate a wave that defies those very laws? There are several mechanisms at play, and none of them fully explains all the observations on their own. The first mechanism is constructive interference. Multiple wave groups of varying lengths and directions converge at a single point, aligning in phase, resulting in their amplitudes adding together. For a brief moment, a wave emerges in one spot of the ocean, towering 2 to 3 times above the background swell. It's akin to 10 voices, all speaking at once, suddenly harmonizing on a single syllable for just a fraction of a second. A fleeting surge, then it vanishes within seconds. This mechanism accounts for rare, isolated peaks. However, it fails to explain why such occurrences are more frequent than linear theory predicts. The second mechanism is non-linear interaction, or modulational instability. This is a deeper process. At high amplitudes, waves cease to act independently. They begin to interact, exchanging energy. Energy redistributes from numerous average waves to a few extreme ones. A wave literally sucks energy from its neighbors, growing to an abnormal height at the expense of the surrounding wave field. This process is described by the nonlinear Schrödinger equation, the same mathematical framework used in quantum physics to describe particle behavior. Ocean waves and quantum particles are governed by the same mathematics, a fact that continues to astonish physicists. The third mechanism involves interactions with currents. When waves move against a strong ocean current, like the Gulf Stream, the Agulhas Current, or the Kuroshio, their length shortens while their height dramatically increases. The energy of the wave, spread across a long, gentle profile, concentrates into a short, steep one. The current acts like a lens, focusing wave energy into a narrow zone. The southeastern coast of South Africa, where the powerful Agulhas Current collides with storm waves from the Southern Ocean, is one of the most dangerous places on the planet, precisely for this reason. Dozens of vessels have sustained severe damage here from abnormally steep and high waves. Now, what does a killer wave do to a ship? A modern cargo vessel is designed for specific calculated wave conditions. For the North Atlantic, the significant wave height is 11 to 12 meters, with a calculated maximum for individual waves around 20 meters. The hull, fittings and superstructure are all engineered to withstand these loads with a safety margin. A killer wave at 25 meters exceeds these limits. Here's what happens next. First, there's the impact pressure. Slamming. The crest crashes down on the hull. The pressure reaches 100 tons or more per square meter. It's an instantaneous impulse, just a fraction of a second, but that's enough to deform steel plates that are 30 millimeters thick. The bow superstructure crumples like cardboard. The bulwark, a steel barrier on the deck, is swept away. Deck equipment is ripped from its foundations and hurled across the deck. The second factor is the green water. A wave towering 25 meters crashes over the deck of a vessel with a 15-meter freeboard. This is not mere spray or foam. It's a solid mass of water, thousands of tons, thick enough to move horizontally at the speed of the wave itself. It floods the deck from bow to superstructure, pressing down on hatch covers with a force they were never designed to withstand. The hatch cover, constructed from steel plates and stiffening ribs, is engineered for a specific distributed load. The impact of the green water creates a dynamic load that exceeds the static design by tenfold or more. If the cover fails, deforming, losing its seal, water rushes into the hold. The hold fills up. Loss of buoyancy ensues. The center of gravity shifts. Stability is compromised. The third factor is the extreme bending moment. An ocean-going vessel measuring 300 to 400 meters is essentially a beam resting on waves. As a long wave travels along the hull, one part of the ship is supported by the crest, while another hangs over the trough. The hull bends. This is a standard load. Engineers refer to it as hogging and sagging, and the hull is designed to handle it. However, the steepness of a rogue wave, the ratio of height to length, is abnormally high. It creates an extreme height differential over a short distance. The bow of the ship may be perched atop a 25-meter crest, while the midsection dips into the trough. The bending moment at the average cross-section exceeds the calculated limits. The deck beams, the upper flange of this steel beam, experience tensile loads that surpass the yield strength of steel. Plastic deformation begins. If the load does not decrease, a crack initiates. The crack in the deck propagates down the side. The hull loses its integrity. The ship breaks apart. Consider the MV Derbyshire. In 1980, this bulk carrier, with a dead weight of 169,000 tons and a crew of 44, was the largest British merchant vessel of its time. It vanished without a trace in Typhoon Orchid, south of Japan. No distress signal, no debris on the surface, no oil slick. It was as if a 294-meter-long ship had simply ceased to exist. An investigation that spanned 20 years and required 2 deep-sea expeditions with submersibles eventually pieced together the story. An extreme wave, or a series of waves, damaged the bow ventilation pipes and the forward hatch covers. Water surged into the 4 compartments. The bow became overloaded. The ship lost longitudinal strength and broke apart. This marked the largest loss of a British merchant vessel in peacetime. Then there's the MV Estonia. In 1994, this ferry was on its route from Tallinn to Stockholm when 852 lives were lost, one of the largest maritime disasters in Europe since World War II. The bow visor, a massive steel flap that closes the vehicle ramp, was ripped off by the extreme waves of the Baltic Sea. Water flooded the car deck. Thousands of tons of water, freely shifting from side to side, compromised stability in mere minutes. The ferry capsized and sank faster than most passengers could reach safety. But this raises a question. If rogue waves are real, why not build ships with a safety margin for any wave? Here, the economics of global shipping begins to push back. Every millimeter of additional hull thickness translates to thousands of tons of steel on a large vessel. Thousands of tons mean additional draft, increased fuel consumption for each voyage, and reduced cargo capacity. A ship designed to withstand 30-meter waves will be heavier, more expensive to construct, and less efficient to operate than one built for 20-meter waves. The difference in construction costs can reach tens of millions of dollars. The difference in fuel consumption amounts to millions each year. This is critical for a fleet of 50,000 merchant vessels, the number that makes global trade possible. The key question here is probability. A 25-meter wave might never encounter a specific ship throughout its 30-year lifespan, or it could strike on the very first voyage. Design standards are based on a probabilistic approach. The structure is engineered to withstand loads with a certain likelihood of exceeding them during its service life. A rogue wave, however, lies beyond these calculations. It exists in a zone where the probability is low, but the consequences are catastrophic. This is a conscious compromise. Designing every ship for the worst conceivable scenario would render global trade unfeasible. Designing for the average means accepting that a certain percentage of vessels will face extreme loads, and some will inevitably be lost. Now, let's return to the bridge. A storm, the Atlantic. You perceive this storm differently. Beneath the chaotic surface lies non-linear physics, capable of conjuring a wall of water at any moment that exceeds everything your ship was designed to handle. You can't predict it. No model can forecast a rogue wave at a specific point in the ocean. You can't see it on radar. It materializes 1 or 2 miles away, and at a ship's speed of 15 knots, that gives you less than 5 minutes to react. You can't build a ship that can guarantee survival against it. Doing so would make global trade impractical. All you can do is understand the corridor in which your ship exists. The calculated maximum wave height for the North Atlantic is around 20 meters. The hull safety margin is 20 to 30% above that estimate. This allows it to withstand a single wave up to 24 to 26 meters without critical damage. Beyond that lies a zone of uncertainty, a realm where engineering calculations end and loss statistics begin. Within this corridor are hidden lines of defense that passengers and shippers remain unaware of. Strain gauges, deformation sensors installed at critical sections of the hull, provide the captain with real-time bending load data on the bridge monitor. If the values approach permissible limits, course and speed are adjusted immediately, even before the metal begins to fatigue. Satellite altimeters measure wave heights from orbit and relay data to route planning centers. Meteorological routing systems chart courses that avoid high-risk areas, regions of strong currents, zones of wave system convergence, areas with abnormally steep waves. This isn't a guarantee of safety, but every degree of altered course, every knot of reduced speed shifts the odds in favor of survival. It's a cumulative effect of small decisions that, together, save ships. And therein lies, I believe, the haunting beauty of ocean engineering. A ship in the ocean is not an object fortified by an absolute safety margin. It is a structure existing within a probabilistic space, designed for what is most likely to happen, not for what could occur in the worst-case scenario. Because the worst-case scenario, a 30-meter wall of water appearing out of nowhere in 20 seconds, would make every ship on the planet prohibitively expensive and impossibly heavy. Every vessel crossing the ocean carries this quiet compromise between strength and cost, between safety and economics, between what we can calculate and what the ocean can conjure. And every successful voyage is not a mere coincidence. It signifies that the balance has worked this time. And here's what I've been pondering. We've discussed the waves that assault the ship from the outside, but there's a threat that brews within the hull over the years. Corrosion, fatigue cracks, the invisible loss of steel thickness. A process that over 20 years transforms a sturdy structure into a fragile shell. How does a ship age? And why do vessels that have passed all inspections sometimes break apart? I've created a separate video delving into this in detail. You'll find it on the channel,